All right, so first, I got a request to go over a couple of questions from the homework, so let's talk about those. The first one was number 7. This is from the homework last time, which dealt with areas of regular polygons. Okay, so number 7 says 2 adjacent vertices of a regular hexagon are at 0, 0, and 3, 4. Okay, so if you draw a little picture here, the point 0, 0 is here, obviously. 3, 4 is like here or something, right? 3, 4. And they're telling you that these are adjacent vertices of a regular hexagon. So you can picture this hexagon like kind of sitting in the coordinate plane like this. It could be going the other direction also. It really doesn't matter at all. The point is that the length of one of the sides is 5. Right? I got that just by using the Pythagorean theorem. This is a 3, 4, 5 triangle. Like if you go over 3 and up 4, then this diagonal must be 5. Everybody okay with that? So essentially the question is, what's the area of a regular hexagon where one of the sides has length 5? I did a problem just like this in class, but I used 10. It's the exact same problem though, right? If you want to find the area of this hexagon, you just need to find the area of one of these triangles formed by 2 consecutive radii and multiply it by 6, since it's a hexagon, right? So the area, the total area that I'm looking for is really the area of that green triangle times 6. In addition, it's a hexagon, which means that what kind of triangle is that green triangle, actually? It's equilateral. Right? That's true for hexagons, which is why if you look at this homework, most of the problems are hexagons, because they like to on the Regents exam, these are old Regents questions, they like to ask questions that involve more than one topic. This is a question that involves more than one topic. It involves area of regular polygons, but it also involves, do you remember things about special triangles and equilateral triangles and stuff like that? And that's what this problem's about. So if you think about this green triangle right here, side length 5, it actually is equilateral, so all the sides have length 5. And if you were to try and calculate its height, you could use the properties of 30, 60, 90 triangles. This is 2.5 or 5 halves. This is also 2.5 or 5 halves. So what's the height of that triangle then? If you know the short leg of a 30, 60, 90 triangle, what's the length of the long leg in relation to that?
5 halves times the radical 3.
Exactly. Yeah. This height is going to be 5 halves times radical 3. So if we're trying to find the area of the entire hexagon, it's the area of one of these triangles, which is 1/2 base, which is 5, times 5 halves radical 3, that's the height of that triangle, times 6. Okay? They don't say in the problem to round anything, so they wouldn't expect you to round anything. And this is not multiple choice, so they want the answer as a radical. So if you just look at what you have here in terms of numbers, we have, this is really 5 halves times 5 halves, right? So that's 25 fourths, radical 3 times 6. And then you can multiply 6 times 25 fourths, which is like 6 over 1. So this ends up being 150 fourths, radical 3. And you can simplify the 150 fourths if you want to by dividing them both by 2. You get 75 halves. And they don't give you any units. This is just on an XY coordinate system, so you can just say square units. And that's it. Okay, any questions on that? Number 8 from the homework, it says a regular hexagonal box. So a regular hexagonal box with square sides. That means that the top is a regular hexagon, the bottom is a regular hexagon, and each of the little side panels, there'd be 6 of them, are squares. That's what they're saying, right? So if you try and draw a picture of that, look, Ben, it looks like this. It has like a hexagonal top and bottom, so maybe like this. And then square sides, like this. So each of these side panels is a square. That's a regular hexagonal box. Okay? And it says, what's the ratio of the area of a side to the area of the base? Okay, so what I would do here is, since they don't give you any lengths or measurements, just make one up. It doesn't actually matter. You could say each of these sides has a length of 100. Or you could say each of these sides has a length of 1. Or each of these sides has a length of 5, or whatever, and you're still going to get the same ratio of areas. Does that make sense? The ratios are going to be the same whether you make up lengths that are equal to anything, right? So I'm just going to pick nice convenient numbers. So a nice convenient number would be 2. Now, why am I saying a nice convenient number is 2 and not 1 for the length of a side? It's even, and that's a good thing, because if I'm trying to find the area of one of these little triangles here, and I cut it in half, isn't it better to cut in half 2 than it is to cut in half 1? I think so too. So that's what I'm going to do. I'm going to say each of these sides has a length of 2. It could be 2 inches, 2 feet, 2 yards, whatever you want it to be. These are all 2, right? Because these are squares and a regular hexagon. All the sides have length 2. Right? So what's the area of the square, of square side? Yeah, it's just going to be 2 squared. 2 squared, right? And the area of the hexagon is just going to be the area of that red triangle times 6, right? And if I take out this red triangle out of context like I did before, this is 2, 2, 2. Because it's a hexagon, this is an equilateral triangle, right? That's why they did this as a hexagon problem. When I split it down the middle, this is 1 and this is 1, what's the height? Radical 3. Nice, easy number, right? So the area of the hexagon is 1/2 base, which is 2, times height, radical 3, times 6. Well, the 1/2 and the 2 just cancel each other out. So I end up with 6 radical 3. So the area of the side wall square is 4, and the area of the base, the hexagon, is 6 radical 3. The question says, what's the ratio of the area of a sidewall to the area of the base? Well, the ratio of the area to the sidewall to the area of the base would be 4 to 6 radical 3. Now you can think of this as a fraction, 4 over 6 radical 3, so it can be simplified in the same way that you would simplify a fraction. Like, I could say this is really, like, I could reduce the 4 and the 6. This would be 2 over 3 radical 3. And that's actually one of the choices, 2 over 3 radical 3. They wrote it as 2 to 3 radical 3. They wrote it that way. And that's the answer. It's choice B. This is multiple choice. Everybody understand that? Okay. Any other questions on that homework? All right. All right, so today we're going to talk about geometric probability. So I'm not sure how much, if any, probability you guys have ever done. So I'm just going to pretend like you don't know anything about probability at all for a second, okay? I'm sure you do know something about probability. But in general, the probability an event will occur is equals the number of ways the event can occur divided by the number, I'll say the total number, sorry, the total number of equally likely events. Okay, that's generally the formula for probability. It's the number of ways that an event can occur divided by the total number of equally likely events. So for example, suppose you roll a die. Roll a die. Single die, a regular six-sided die. Okay? The probability of rolling a 1 would be 1/6, because there's only one way you can roll a 1, roll the die and it lands on 1, and there's 6 equally likely possible outcomes. So the likelihood would be 1/6. That makes sense, right? Suppose you pick a card. Randomly from a deck. Okay? A deck of cards has how many cards? 52, right? 52 cards. If you want to calculate the probability of selecting a king, the probability would be 4 over 52, right? There's 4 ways to select a king. It could be the king of hearts, the king of clubs, the king of spades, the king of diamonds, 4 ways. And there's 52 equally likely outcomes, all 52 cards in the deck, right? If I wanted to calculate the probability of selecting a face card, we define face cards to be jacks, queens, kings. Don't include aces, those aren't face cards. Then there would be how many possible ways of that occurring? 12, right? It would be jack of the 4 different suits, queen of the 4 different suits, king of the 4 different suits. 12 ways. So this would be 12 over 52. If we wanted to calculate the probability of selecting a spade, what would be the probability of that occurring? 1/4, or 13 out of 52, or 1/4, right? There's 13 spades in a deck, ace through king, right? Or 2 through ace, or whatever you want to say. 13 ways of selecting a spade, 52 total cards in the deck, and that fraction simplifies to be 1/4. So in general, this is how you calculate probability, right? Total, it's the number of ways that the event can occur divided by the total number of equally likely events. They have to be equally likely events. You can't have one event that's more likely to occur and use this formula. It's a little more complicated than that, okay? But this is generally the way that it works. So the probability always ends up being a number between 0 and 1. It can't ever be greater than 1, because then you're saying that the total number of events is actually less than the number of events that you want to occur, which makes no sense, right? So there's no way that the probability can ever be greater than 1. All right, so when you're talking about geometric probability, you can think of it the same way. Like, for example, suppose I have a spinner. And the spinner looks like this. It's split up into 5 equal-sized regions. Okay, and suppose we have like A, B, C, D, E in each of the different regions. So you know how a spinner works? There's like a little arrow, and you flick it, and it goes around and it lands on one of the regions, right? And pretend like if it lands on a line, you just do over or something like that, right? So if you wanted to calculate like the probability that it lands on a vowel or something, what would that be? Vowels are A, E, I, O, U. 2 out of, yeah, 2/5. This would be 2/5. And you're really using area to ascertain that it's equally likely that it lands on any one letter, right? Because each of these areas are equal, right? So there would be, like, if I thought of this as like, I wanted it to land on one of these shaded regions, right? There would be a 2/5 likelihood that that would occur because 2 out of the 5 little slices of pie are shaded, right? But it's based on area why that's true. So let's look at a different type of question then. What if you have just a weird looking dartboard? And suppose the dartboard just looks like this. It's just like a rectangle that's split up into regions like this. And each of the regions are equal size. Okay? And you have a pet cat that you train to throw darts. Okay? Your cat is trained to throw darts, and if the cat misses the dartboard, then it's just a do-over. All right? What's the likelihood that your cat will hit that shaded region? Yeah, this would be one. How many pieces? 9. 1/9. There would be a 1/9 probability, right? So the probability of hitting the shaded region would be 1/9. And in general, the way I did that is the same way that I calculate normal probability. I calculated the area of the shaded part and I divided that by the total area. Right? It's the number of ways something can happen divided by total number of equally likely outcomes, just put into like an area context. Does everybody understand it's kind of the same thing that we were doing before? We roll the die, it's the same thing, right? So nowhere did I actually calculate an area though, right? I never actually figured out what an area was because I didn't have any actual measurements. I could have like assigned some lengths and said, okay, let's calculate areas, right? Like I could have said like let's suppose this is 2, and this is 1, 1, 1, 1, 1, 1, 1, 1, 1, right? I could have actually calculated the areas and said, okay, so the shaded area is 1 times 2, 1 times 2, and the total area is 9 times 2. And I could have just simplified this fraction and said, oh, okay, so the probability is 1/9. But it actually really didn't matter what the lengths of the sides were. I could have said, instead of 2 and 1, I could have said, what if this is 20 and 10? Or what if this is 5 and 3? Or something like that. It would have come out the same way, right? Like, for example, what if I said this was 5 and these are all 3, right? Well, what would the probability have been then? This area right here would be 3 times 5. And the total area would be 27 times 5. I would get the same answer. The 5s would reduce, the 3 and the 9 would simplify to be 1, 9. I'd get the same answer. It doesn't matter what I assigned to be lengths. It just turns out to be the same thing, same ratio, the same probability. Okay? So what if it's a different type of problem? What if the dartboard looks like this instead? What if it's a square with an inscribed circle? A square with an inscribed circle, and you want to find the probability that it lands outside the circle, within the square. So that's the bullseye, is the stuff that's shaded. It wouldn't matter if this target is as big as that wall, or if this target is this big. The probability that it lands in the shaded part would still be the same. You agree? Because the ratio would still be the same. So all you're going to do here is you're just going to calculate the shaded area divided by the total area. Now, unfortunately, they didn't give us any lengths. So I'm just going to make up a length, okay? And it doesn't matter if I said the side of this square is 100 yards or if the side of the square is 2 millimeters, right? It wouldn't matter. So I'm just going to pick a nice convenient length. What would be a nice convenient length for the side of the square? What's that?
2.
Yeah, why not 1? You're right.
Because you have to get the radius.
Exactly, right? Don't pick a number that when you cut it in half, you're going to have to work with fractions the rest of the way. That's torture, right? So pick a number that's even so that when you cut it in half, it's still a whole number and you can like deal with whole numbers. It's easier that way. So I'm just going to say this is 2, which means the radius of the circle is 1. How can I calculate that shaded area then?
Find the area of the circle, and the area of the whole square, and then subtract.
Yeah, right? This is composite area. This is actually on the test prior. Calculating composite areas, either by addition or by subtraction. In this case, we would just subtract. So really what we're going to do is we're going to calculate the shaded area divided by total area, which just in symbols, it's going to be, the shaded area is really square minus circle, right? And the total area is square. That's really what I'm doing. I'm going to calculate the area of the square minus the area of the circle divided by the area of the square, which is the whole area of the whole dartboard. So this ends up being 2 squared, that's the area of the square, minus pi r squared, pi times 1 squared, divided by 2 squared. So I could simplify this to be 4 minus pi over 4, or I could actually like find a percentage or a decimal. I could say 4 minus pi divided by 4, which ends up being 0.21. So there's actually a 21% chance that my cap would hit the desired area on the dartboard. Right? Sometimes it's helpful to change probabilities into likelihood. Like there's a 21% likelihood that this would occur. Okay? I have a really talented cat. Let's try another problem. What if the picture looks like this? What if it's a square dartboard again? This time there's little quarter circles in each corner. This. So that's what my dartboard looks like. And I want to calculate the probability that it lands in one of these shaded parts. That's the bullseye. A weird dartboard, but that's what it looks like. So it's the same deal, right? It's just going to be the shaded area divided by total area. Well, the shaded area is just 2 quarter circles, which is essentially a half circle, right? I'm just going to draw like a little half circle here. And the total area is a square, right? I'll leave it split in half so you can see that there's 2 quarter circles. So again, I'm going to pick a nice convenient number like 2. Do this. The area of a half circle would be 1/2 pi r squared. The area of a square would be the length of a side squared. So this is pi over 2 over 4, which is pi over 8. Right? Dividing by 4 is the same thing as multiplying by 1/4. So pi over 8, if I wanted to get a likelihood on my calculator, you just do pi divided by 8. And I get there's a 39% chance that this occurs. Everybody understand the idea? So if you're trying to calculate geometric probability, they're going to give you some either shaded region or otherwise indicate like the desired part where you want to end up. And you want to just calculate the area of that desired part, or the shaded part, divided by total area. And that's going to give you the probability that a randomly thrown dart, they're not all going to be dart problems, but they're all kind of like dart problems. They're all the same idea. That a randomly thrown dart lands in the shaded area. Any questions about that? Okay. So the homework, once again, is on Google Classroom, and it's called Geometric Probability. Also due Monday, just like a normal assignment. And that's it. Okay?